Oh, Dan's gone. He looks like my icon.
Okay, I'm recording it now.
Okay.
I'm recording, and I'm also going to say farewell for the moment.
Sounds good. And are you making me host now?
I think I'll keep it as host just to make sure that the recording goes through properly.
Great. Okay.
Okay, and if you for some reason you need it back, let me know.
Okay. Sounds good. Thank you, Nancy.
Thank you, and have a great meeting.
Thanks. Bye. Oh, am I able to, Nancy, are you still, can you still hear me?
Yeah.
Am I able to end the meeting?
Yeah. You
Okay.
should be able to end the meeting, but I expect to be back by then.
Okay, great.
Yeah.
See you later.
Okay.
I'm bummed that I can't get a picture up there.
I couldn't either, Dan, and then I went on and downloaded the updates. But that takes a little bit, so, and it might kick you off.
Well, I may just leave it as this anonymous looking
The shadow figure.
Yeah, I feel bad about that, but I suspect that we shouldn't be. That we might get in trouble if we have the video on in here. Sorry, everybody.
It's okay, man. Don't worry about it. We know that you work behind the fence.
Pay no attention to the man behind the curtain.
Hi, Vic. Hi, Diane.
I'm back.
Vic, that was such a cool thing that you sent with the connection between how the whales migrate.
I've actually got the researcher. He's coming up to the school, and we're going to go through how magnetometer works and show him what we've got. He was really interested in it.
That's so cool.
Yes, it is.
We'll just give it a couple more minutes. I know that some other people were planning to attend, and then we'll get started. Anything exciting happening in you guys' world this week?
The whales
There's a lot of consternation there.
the whales are still here. They haven't moved to Hawaii yet.
Uh-huh. Now, Sally, where are you? Oh, Sally's off.
Oh, Sally, you're on mute.
I'm from New Hampshire.
New Hampshire, okay.
And
Vic,
you are?
I'm at Berkeley.
Okay. What's your first name?
John.
John, okay.
Sorry, I'm so used to doing telecons with the project where we're not, well, we are on a first name basis, but it's everybody kind of for themselves. So, yeah, I'm one of the instrument scientists on the Van Allen probes.
Oh, cool.
Yeah.
All right.
So, and Vic, where are you?
Petersburg, Alaska.
Alaska, okay.
And Diane's from Florida.
Yeah, so Diane conveniently put it on her tag. I always joke at those, like, hello, hello, my name is whatever. You know, they're like the best things.
Oh, Diane, did you and your husband get the answering machine recording from Wait, Don't Tell Me?
No, not yet. He wrote a script, and what will happen is Carl Castle will record it, and it'll be sent back to us as a CD, so that if our phone blows up at some point in the future, we can still have it.
Oh, that's neat.
And yeah, so we had a lot of fun with it.
I don't know if everybody knows about that. Do you want to fill them in?
If you guys know Wait, Wait, Don't Tell Me, it's on NPR, and my husband and I are complete addicts. And we've been talking about calling in for weeks. And a couple of weeks ago, my husband called in, and he made the connection. And so he was on the show about 2 weeks ago, and it was just really, really fun.
What game did he play?
What is it? Who am I this time? It was, who is Carl this time? So it's
right.
The opening segment. So
I'm jealous.
Well, what was so fun about it was, what edits down to about 3 or 4 minutes of airtime was 30 or 40 minutes on the phone. Because that when they all go on these riffs about topics, and the audience in Mobile was just crazy.
That's
I
great.
thought it was a live show.
Well, it is it's taped. It's done live on Thursday night. And so I've always been just surprised at how funny they are, all the stuff. And what happens is there's 5 minutes of conversation, and they take the best, minute. So it's not quite as brilliant. They're editing the brilliance.
Well, we're about 5 minutes after our start time, so let's go ahead and get started to give Dr. Bunnell and Dr. Smith enough time to go through all of the things that they were going to show us. It's really a lot of exciting stuff. Thank you so much, you guys, for planning this out so well and putting together this list of resources that you're going to share with us today. I'm going to turn things over to Dr. Bunnell and Dr. Smith, and I think that if you guys go to share screen, whoever would like to start first sharing their screen, and then you'll have the control.
Okay. Thanks, Dawn. So, Dan, I'm not sure how you want to share this out. Do you want to start with the navigation on the Science Gateway stuff?
That's okay with me. Okay. I think we have that at the top of our list, right? In fact,
that's right.
All right, so I will share my screen.
Were you guys able to get the walkthrough guide that John just sent out? I posted it on Wigio, but I don't know if you guys had a chance to see it. It just went up about an hour and a half, 2 hours ago.
Got it.
Great.
I did too.
Sounds good.
Cool. Yeah, essentially, I mean, just to sort of give you an idea where we're going with that, Dan and I's plan is to sort of walk through that. And what I wanted to give you all was all the URLs and clicks and particular selections that we're going to make along the way, so that as you guys are thinking about what you've seen and how you might use it, for classroom purposes or other purposes, you've got a ready reference for that.
All right, can everybody see my screen? I have, it should be showing the Van Allen Probe's website.
Yep.
I can see it.
Everybody else okay? Maybe everybody's on mute.
I can see it too. Okay. I think we lost Sally for a minute, but she'll probably be calling back in.
All right. Should we wait a minute, or should we just push ahead then?
You can go ahead and get started. It's recording.
Okay. This website here is obviously the main mission website, and this is where there's the news and all that stuff shows up. But we're going to talk about the data, and so if you want to get to what we call the Science Gateway, there is a big tab right here, and you can probably see my cursor circling around it that says Gateway. So I'm going to click on that. And that opens a tab to a different website, which is called the Van Allen Probe Science Gateway. And this is where there is lots of cool stuff to see. Let's see. John and I put together this little outline here. I want to make sure I hit the bits that we talked about. So the first thing here you'll notice is we have a whole bunch of different, like 10 different things to write on the front page that are sort of the real important bits. But there's a big long menu on the side here. I don't know, and I think our "Where is the Van Allen probes" button disappeared for some reason. But there used to be one. But if you go down, there's a thing on the side here that says "Where are Van Allen probes?" And slowly but surely, this because it's the Google plugin. This is a Google Earth plugin. This is kind of wacky because it shows it holds the Earth still, and so it looks like the paths of the spacecraft there. But I like looking at this projection here. It kind of shows you where the spacecraft are. Like right now, it looks like they're right over South America, and you can choose different projections. You can see there's a different Mercator projection, and you can also take a look at orbit plots in different reference frames. This one makes a little more sense here. Here, the circle in the middle, of course, is Earth, and you can see the elliptical orbits of the spacecraft. And RBSPA is in red, and RBSPB, or Van Allen probes A and Van Allen probes B, B is in green. And you can actually go up here, and if you want to, there's a click here for Orbit Plotter. You can actually pick what days you want to, what orbits you want to plot for which days, and you can pick different coordinate systems to look at. So that's just, you know, before even looking at data, this is just to get an idea of if you wanted to see where the spacecraft were at any given point. We have the tools to do that in lots of different coordinate systems. What is it we wanted to look at, John? Let's see. Some notes here. The GEI coordinate system. I mean to have the actual thing up here. In the GEI frame, that's fixed to the stars. So that's like if you're looking down on the Earth, you're not rotating with the Earth. So that's why you can see the orbits that look elliptical like you want. But if you wanted to see what it looked like if you were holding the Earth still, so you were rotating with the Earth, then that would be the geo frame. And that's why it looks all spirograph, because we are in a rotating reference frame, so it wiggles the orbits all around there. The other thing that is kind of interesting, what is the order we did this in, John? Do you remember?
Yeah, so we did it in the walkthrough. We started in GEI because that gives, you know, basically like a real canonical picture of an orbit. And it really shows you how eccentric an ellipse the orbit is. You know, you come in within 700 kilometers of the surface of the Earth at perigee, and you go all the way out to, I believe it's 37,000 kilometers at apogee. In the bottom panel, you can see that the orbit is tilted with respect to the Earth's equatorial plane by about 10 degrees, and that's on purpose. We do that to basically tailor what parts of the Earth's magnetic field we visit with the orbit. And then also what it shows is the separation of the two vehicles along their nearly common orbital path. And that's something, you know, again, that we designed the mission. We did that by design so that over time, they basically drift apart and drift back together again along the orbit. This is, I think we talked about it a couple, I guess it's almost 2 months ago when I did the mission introduction. This is this idea of the probes lapping each other. Basically, RBSPB orbits a little bit faster than RBSPA, and over the course of 70 days, they get all the way apart so that one of them's at perigee, the other one's at apogee, and then they come back together again, and they're within a few thousand kilometers of each other. And what that allows us to do with the instrumentation on board is look at features in the magnetosphere at different scales and across different separations, either in radius or in local time. So so an example of how you might use this is if at the point in your classwork that you're talking about orbits, you can show them here, this is what this looks like, and and if you want to talk a little bit about how the different vehicles move, you can do that. Going to the GEO frame. So in this frame, we're still sitting up above the ecliptic, but we're spinning with the Earth. And so this is sort of the path that gets traced out in space by the vehicles, if you're moving with the Earth. And, as Dan mentioned, it's kind of spirograph-like or figure-8-like. And a question to ask is, why does that happen? Just by going from one reference frame to another, why does that happen? And there's a description of that in the walkthrough, but really it has to do with how fast the satellites are moving relative to the Earth, when you're at perigee versus when you're at apogee. When you're at perigee, they're moving a lot faster than the 1,000 or so kilometer, or 1,000 or kilometer per second that you get at the equator of the Earth. The satellites are moving a lot faster than that, so they're moving counterclockwise relative to the Earth. But then when you get out to perigee, they're moving slower. That's a standard thing that happens in orbital dynamics. And so they end up going the other way, and so you get this sort of figure-8. So again, I think I might have had issue with this in high school, sort of figuring out how all this works out. But again, it's an interesting sort of thing to talk about reference frames and how different stuff looks compared to for different observers.
We also wanted to show the magnetic mapping tool, but before we do that, I should show this animation, right?
Yeah, that's right. So, what this leads to is, part of what we do with RBSP and other missions is we use them as remote probes out in the magnetosphere, and then try and look and see what sort of effects are going on down on the Earth related to what's going on further out in the magnetosphere. And for the kind of phenomena that we look at, it has more to do with where the magnetic field lines go than where in the sky the satellite is. So the movie that Dan's bringing up shows some of the particle motion. Yeah. So under the influence of a magnetic field, a particle will sit there and it'll gyrate around the magnetic field line. That's what this little red particle's doing. Then it's also free to move along the magnetic field line just like it is. It sort of follows this helical path along the magnetic field line. But then it also does, this is much more complicated, and it gets all added together. There's other drifts and things that are going on. But the gist of it is that here you can see this depiction of a slice through the Earth's magnetic field and magnetosphere, and sort of a pictorial representation of the intensity of particle flux, the number of particles per square centimeter per second that you would see in a particular energy range. And so this is probably the outer electron belts. And what you should get from this, and how this relates back to this question of the orbital placement, is the particles that we see being influenced by electromagnetic phenomena out further in the magnetosphere they don't go straight into the Earth. They follow the magnetic field line and come down at higher latitudes. And that's what the magnetic field mapping tool shows you. It allows you to pick out a model for this magnetic field and follow that field line down either into the northern regions or the southern regions and decide what's going on, you know, where you would want to put an observer to see if there was an effect. Now, that at the end of the talk last time, we talked a little bit about the barrel campaign, and this is a balloon campaign where they're down in Antarctica. Oh, great, it's up and running. Okay, cool. So let's see, why don't you, let's see, so we set it on large. So anyway, I think if there's a way that we can get, spend some time. Dan, if you could click on the extent and time of the footprint and see if we can get a longer chunk of time. Yeah, 20, yeah, that's good. Okay, so what's going on here is, I mean, again, you can sort of see these small loops at high latitude, and those small loops at high latitude correspond to when we're out at apogee, far away from the Earth. And those magnetic field lines that are far away from the Earth at the equator map to higher latitudes on the surface of the Earth. And then sort of going off the edge of the screen, that's the passage to inward to perigee, and those field lines map to much lower latitudes until eventually we get in towards 700 kilometers, and they hardly map that far away from the equator at all. These little loops, maybe if you could switch to the south projection. Yeah, excellent. Okay, so if you look on the right-hand side of the map, where those loops, the end of the red and the blue loops are hooking there, that's actually right near where the barrel balloons were getting released in the campaign last winter, and it's where where they will be released in this upcoming campaign from the Halley Bay and the Sinai station there. And what happens is you release the balloon, and the balloon has detectors on it that allow it to see the effect of high energy electrons coming down into the upper atmosphere. And so what we can do is we can have the RBSP spacecraft far out in the magnetosphere watching what's happening, and then the barrel payloads down low watching what's happening to see if the sorts of things that are going on out in the magnetosphere have an effect and dump energetic particles out of the radiation belts. So again, I mean, the level of abstraction here maybe is a little bit high. I don't know, but I think the idea of comparing satellites that look straight down at the Earth, like sort of the more Earth observing satellites, that are like looking at the ocean surface or looking like land. I don't know. You guys are of a generation, so you know about Landsat and those beautiful pictures that you get in the National Geographic showing landforms and stuff. Now that's a satellite that's looking straight down at the Earth and telling you, Earth science stuff. Whereas here, it's a much more indirect kind of connection between where what you're measuring out far away from the Earth and where it lands down onto the surface of the Earth. Anyway, so those are sort of the orbit tools and things that are available through the Science Gateway. Before we go on to sort of more data stuff, and as Dan's showing you, there's a lot of flexibility in this interface. You can pick different days, you can do different time steps through, you can change what magnetic field model you're using. And there's it's a whole variety of things that you can do with this. And sort of really what I want to do is just expose you to this, and then let it percolate and see what you guys think you can do with it. So, any comments or questions on what we've covered so far?
I've got one. When you're looking at these, I'm looking at these blue and red loops. And I'll notice that your vector arrows, 1, 2, 3, 4, 5, 6 of them on that loop.
Yep.
Would I interpret that correctly to say right in the dead center of that loop, the actual orbit speed of the satellite and the rotational speed of the Earth match?
Yes, that's exactly right.
Okay.
Yeah, so like and if we, if you go back to the spirograph plot where the loops of the figure 8 cross, that's the same thing.
Okay, so it's based because you're using the Earth as a frame of reference, but you're not on the Earth, you're above it.
Yep.
And so the Earth is spinning. Okay, that's nice.
Isn't that cool?
That's cool.
Yeah. So, and I mean, the interesting thing about it is that the geosynchronous satellites, they wander in the same way. So they actually, if you don't put them in a perfectly circular orbit, there's, when they're at perigee, they're moving a little bit fast. When they're at apogee, they're moving a little bit slow, and they wander east and west because of that. And then if they're not quite in the equatorial plane, they'll wander in sort of a figure 8 above and below the equator. And you think, wow, how can it be doing that? And really, it's just following an ellipse out in space, but you're viewing it from a rotating frame, and that makes all the difference.
Frame of reference. Thank you.
So the other cool thing about this, if I believe that these little arrows on the paths are ticked off. Let's see, what are the tick marks on here? I think I don't know if they're 30 minutes or an hour, but what you can get is that you get a sense for how fast the satellite is moving. So it's moving much more slowly at apogee, and so it lingers for hours in these small loops at high latitudes, and then swoops down to low latitudes as it goes through perigee. And it's a really cool feature of this, because essentially we linger for a long time out in very interesting parts of the magnetosphere, when we're at apogee, and then we barrel our way in very quickly, covering a lot of territory and radius when we do our inbound and outbound passes. So it's kind of that's another cool feature of the orbits to think about.
Those tick marks are set to an hour, but you can change them to 10 minutes, 20, 30, or 4 hours.
Yeah.
Could you make a change? Oh, you did. Okay, thank you.
You want 10 minutes, you'll see they'll be really bunched up there.
So anyway, so I think that's a cool and interesting thing. I mean, even there's a lot of stuff. I mean, I think that there are orbit simulators out there that you can get a hold of, and even sort of backing up and thinking about things simply like that. If you're doing something about gravitation and Newton's laws and Kepler and things like that, sort of looking at it and saying, well, here's some actual ramifications of this in terms of geosynchronous satellites, or the Russian analog. It's a name I've never learned how to say. Millennia, I believe, is the right term, where they use a high inclination, high eccentricity orbit that takes advantage of this lingering or loitering at apogee to have it basically hang in the sky above the Soviet Union or Russia for long periods of time for geosynchronous or for communication purposes. It's an interesting thing that comes out of how the orbital dynamics works. Okay. Anyway, let's see. So the next thing. So any other questions, comments that you wanna hit on? No. Okay. Looks like no. All right. So we're going to then go to this near real-time space weather data. And
Pardon.
it's all right. So Dan, let's see. Why don't you you want to start on this, or do you want
Sure,
me to start?
I will certainly talk about this.
Okay, cool.
One of the things that the Van Allen probes does is that they broadcast a subset of all the instrument data, not all of the data, but a subset of the data all the time, except when they're downlinking all the data, which is just for short periods of time during the day. And the reason they do that is it acts as sort of they call it the space weather beacon. And so we can get, if you have a big enough dish, you can tune in to the Van Allen probes and get their space weather beacon data. And what it allows us to do is to get a near real-time glimpse of what is going on in the radiation belts right now. And so there's two stations, one in Korea and one in the Czech Republic, that are providing, a dish and are downloading this data, and they send it to us and we post it on the Science Gateway. And recently, Rob Barnes put together this really cool visualization for this space weather data. What you're looking at here is, obviously, there's the Earth and the elliptical orbits of the Van Allen probes, and there's A and B. And this actually updates every minute in almost real time. And so while we're sitting here, we may see the spacecraft slowly moving along their orbits. And in this big picture in the middle here, when we do have data, because we don't get it all the time, only when one of those two stations is tuned in, so the spacecraft have to be, visible to those antennae. We will get some data, and we grab it like every 15 minutes. So it's not real time, but it's like a latency of about 15 minutes, which is really good. And we overplot it on the orbit here. And what this is just one instrument, actually. We do get space weather data from all the instruments, but right here we're just plotting the REPT instrument, and REPT looks at the really high energy electrons and protons. So the real, the radiation that packs a punch. This is the radiation belts that we're looking at here. And we've plotted 3 channels, because we only get 3 channels for the space weather beacon. You get more when you get the full science data download. But what Rob's done here is he's plotted 3 different channels, and the x-axis, I'm looking at the 3 things on the side here. The x-axis is time, and the far right corner is now. And so if you go backwards to the left, you're looking backwards in time. The y-axis is labeled as L shell. That's basically a measure of how far out from the Earth you are. And it's measured in Earth radii. So an L of 2 means you're 2 Earth radii from the center of the Earth. It's actually as measured in the magnetic equator. So it's if you were in the equator of the magnetic field, the dipole field, then L of 2 or L of 3 would be like 3 out from the center of the Earth there. So it's more or less a measure of how far away from the center of the Earth you are. And so as the spacecraft pass through, we get these strips, and then the color bar tells you the intensity or the flux of the radiation. These channels, you can see, are actually a combination of electrons and protons, because the type of data we get is limited for the space weather, and the amount of time we have to do any kind of calibration or reducing of the data is very quick, because we want to get it out in as quickly as we can. So we can't separate out electrons and protons in this case. So it's sort of a bucket that catches both. The top one is the highest energy electrons and protons. Then there's a middle energy. You can see top one's labeled as 10 MeV electrons and anything bigger than 70 MeV protons. And then the middle is 5 MeV electrons greater than 50 MeV protons. And the bottom one is a lower energy 2 MeV electrons and greater than 20. And these, if you look down here at the 2 MeVs, you can see that there was a belt here in the past. Where's the time? Okay, down at the bottom, you can see this is, if this is now, that would have been 2 days ago. So it's like 2 days worth of data. So for a while there was a belt there, a moderate belt, and for some reason it sort of disappeared. It started disappearing. Then a big magnetic storm hit, and we plotted, for your convenience, the what's called DST, which is an index that measures geomagnetic activity. So this is it's called a storm time index, and when you see a big drop in DST, that means there's a geomagnetic storm, and that's what happened here a couple of days ago. And then it recovers, and then actually we had another one just like yesterday, I guess, and back it comes. Then it recovered again, and you can see that the radiation belts are responding to this. In fact, the 2 MeV electrons seem to have dropped out quite a bit when the storm hit, and then came back roaring with the recovery. And you can see the same kind of behavior in the higher energies as well. Rob's put these cool little, this is just to see further out. And the reason he had done this is this tool he created so we could watch the Juno fly by. When the Juno spacecraft flew by the Earth yesterday, you could sit here, and I did this, you could sit here and watch, and you would watch it creep onto the screen and then slowly move down here and then zip around the Earth, and out it went down this way. And you could see what the radiation belts were doing while Juno was flying through them. And he had just put some zoomed out views here.
You can go back to that, right?
I can. That's a good point. Let me give that a try. So let's see. At the top, you can see that there is a date. Oh, look at that. And there's the Juno path. And I can probably, let's see, when did Juno show up? No, that's too far, Dan. I'll find it. I'm clicking through. You can see that the data is being pasted on there as we go, as it comes in. Oh, and there's Juno. And I'll slow down here. And then I'm just clicking through, and you can see Juno flying by. And you can also see that there wasn't a whole lot of radiation belt in those energies when Juno flew through. So if you were watching, I'm clicking through faster than it actually occurred, but that's what it looked like yesterday, and it was painting on the real-time data as Juno was flying by. So that was pretty cool. And you can see that Juno's still down here in the zoomed-out view.
And just to give you some orientation on this, this is in the so-called GSE coordinate system. So if you reel back up to the big orbit plot there.
Right.
So GSE X, positive direction of X, points at the sun. So the sun is off to the right.
Right. Mm-hmm.
And then GSE positive direction Y points at dusk. And so essentially we're sitting above the North Pole of the Earth. The Earth would rotate counterclockwise underneath us. And so Juno came from sort of the dusk side and actually underneath, and then went out behind us and toward the dawn side. And essentially it was, let's see, that means it's catching up to the Earth, and so the Earth slows down, Juno speeds up, and I can't remember exactly what slingshot it got from it, but it was a significant delta V that they really needed to be able to do the mission.
So even though we created this tool, and by we I mean Rob Barnes, because it was really all him, even though this tool was created so we could watch the Juno flyby, we're going to leave it up here because it's a good tool just for visualization of what's going on in the space weather right now in the radiation belts. And at the very bottom, he put for context the actual science level data up to where we have it, because the science data takes 15 days, I think, from when it's collected before it's usually put up on the website and is available to look at. But this is all calibrated, and the electrons and protons are separated out. And so these 3 channels are 3 different electron channels. And one thing that's kind of cool here is if you look way up, this is the entire mission so far. That's what he's got plotted down here. And so again, the x-axis is time, the y-axis is L-shell, so distance away from the Earth. And so you can see it in the 3.6 MeV electrons and in the 5.6 MeV electrons, you can see the 3 belts that occurred in the first month of the mission. So there's 1, then there's a little bit of a slot region, then there's 2, I guess that's what Dan Baker calls the storage ring, right? Then there's the real slot region, and then here's the inner belt here. And likewise, you can see it not as well, but there it is again. There's the inner belt. Here's the inner belt. Here's the inner part of the outer belt, that slot region, and then the outer belt. So there's that 3-ring structure that then gets hit by, I guess it was a CME or there was a large scale geomagnetic storm that hit and wipes out those radiation belts for a little while. But when they came back with the standard two belt structure and not that 3-belt structure that we were so excited about.
Excuse me, could you slide that slide up a little bit so I can see the bottom of it?
Slide it. I think I got it as far as I can go. Let me see if I can.
Okay, thank you. I can't see the bottom of the bottom one.
All right. I think I have an idea to help me fix that. Ooh, this does not want to let me change the size of the screen. That's kind of interesting. It won't let me scroll up anymore for some reason, but well, I'll tell you what I can do.
Dan, it looked like it scrolled up a little bit.
That's as
Vic,
far as
can you
it'll
see it now?
Vic, if I move my mouse, it'll move the screen around for me. So try moving your mouse.
Nope. It's actually it's worse now. I can just see the top one. Maybe it's my resolution, not yours.
That might be.
We can go on. We can go.
Okay. I'll actually have a place where I can show you a better. I think. In fact, I'll try it right now.
So Vic, you're trying to get a handle on the time scale?
Here's the same.
What I'm trying to get a handle on is how it's layered. And because I'm looking at these and I'm assuming these are the layers where it's red is one of the layers within that Van Allen belt. And I'm just trying to compare at the different energy levels how those layers lay out. Was all I was just looking at.
Understood.
You know, kind of morbid curiosity.
More like, so basically like how the energies are layered in L-shell?
Yes, that's it.
Okay.
This one's not. This tool is. I was just jumping to a tool that we had that I thought would show it better, and unfortunately, it's broken. This is why there's not actually a link to it yet, because I think we're still working on it. Can't seem to get that 3rd belt. That was good omission. All right, there we go. 1, 2, 3. These 3 graphs here are the same 3 that you couldn't see the bottom of before. And with the bonus that I have DST plotted, which is that storm time index. So you can see whenever there's a big drop in DST, that's a geomagnetic storm, you can see that the changes in the radiation belts here correspond with the different dips in DST. And this is start of the mission, I believe. So yeah, that would be at the very bottom. Again, you probably can't see the very bottom of my screen, but each one of these lines is a month, and it starts at the beginning of the mission. So once again, there's 1, 2, 3, 1, 2, 3, that 3-belt structure. You can see this giant geomagnetic storm hits and then kind of wipes it out. This is another, these pictures here, well, eventually when Rob gets this one straightened out too, this will be another thing you can, another way you can go and look at the data. The space weather data is plotted up here as well. And this was done so we could actually compare what the space weather data looks like versus what the actual science data looks like. And you can see that they do compare pretty well. It's not perfect. The space weather data is not as well calibrated. It doesn't have the protons and electrons separated out. And again, we've been using REPT here, the instrument, as sort of our prototype to do these things. But we're going to be able to have these kinds of images for the other instruments as well. And hopefully we'll get not just the particle instruments, but like John's Valley with the waves, fields and waves instruments as well. Although we're still deciding the best way to plot that in this kind of a format.
Dan, I have a question. You mentioned that you mentioned the space weather data versus the science data. Is the difference that the space weather data has protons and electrons and science data only has electrons?
Yes, that is one of the differences. Absolutely. In the space weather data, which is the top 3 plots I'm showing here, has the electrons and protons all together in one bucket, and they're in slightly different and wider energy buckets as well. Whereas the science data is cleaner, it's better calibrated, it separates out electrons and protons. Here we're only showing electrons, but there's also the proton data as well, and there's other energy channels and that sort of thing. So,
are there other differences between the 2 different kinds of graphs?
Also, there's more data gaps in the space weather data because that was only gotten when the spacecraft happened to be over either the Czech Republic's antenna or the Korean antenna. And also, you can't take the space weather data when the spacecraft is downlinking its main downlink to dump all its science data. So there's a lot more gaps in the space weather data. And the space weather data is not something you want to do science with. It's a way for you to look and see what's going on right now, rather than when you want to do science, if you want to answer, physics questions, you want to go back and use the fully calibrated, data that doesn't have the data gaps. There's a couple of data gaps in here, but it's not nearly as bad, you can see, as the space weather is much more coarse. So yeah, so if you're going to do science, don't use the space weather data. Go back and get the real data. But if you're interested in what's going on right now, you go and you look at the space weather data. In fact, we could just look at, for instance, this month, right? So this side, I just expanded out the x-axis when I did that. So this is showing you like what happened in the last couple of days here, all the way back to the beginning, to last month. Now, I said that we have the data for the other. Well, before I move on, does anybody have any other questions about that? Okay. We do have all of the other space weather data for the other instruments. And this page, while this is a little bit uglier, here is, if you want to go and see all of the different space weather data from the other instruments, you can go to this page here. And at the top of the page, we actually have data that's from other places. So this is the top here is KP, which is an index that tells you something about geomagnetic activity. DST, again, is that storm time index. Then we have some stuff about the solar wind, and this data comes in the magnetic field, the magnetic field due to the sun. This is measured by the ACE spacecraft, and so we grab that stuff and throw it up here so you can see in context what the solar wind is doing and what the magnetic field is doing. So that's what's all at the top here. And then we have the spacecraft position, or L shell as a function of time, spacecraft in different coordinate frames, X, Y, and Z as a function of time. See, these aren't as pretty as the orbit plots. These are just line plots, but it's here. And then here's EFW. So this is a electric field in the X, Y, and Z in the GSM frame, and you can see that there's data gaps here because we get some, and then we may only get it for a little while, and then it comes back in view of the other antenna, and we get that one. And so we try and put up as much of it as we get, and hopefully we'll get more stations tuning in and sending us the data so that there won't be nearly this many gaps. Right now we've only got 2 of them, and only one of them is working in real time, in near real time. The other one has got more latency.
So just to sort of jump in and sort of talk about the kind of data, sort of data quality or data coverage issues that Dan was mentioning for the particle data. And here, it's an electric field, and actually there's some calibration issues that we're still working on with this. But it's an electric field that's measured in the frame of the spacecraft. And so there's in essence, you're getting what's going on geophysically, but you're also getting something that's due to your frame, being in a moving frame relative to the Earth's magnetic field. And so there's a large electric field that you get going through perigee. It basically dominates over all of the sort of more interesting geophysical fields. And that's what this, that big swoop there that Dan's pointing at, that's what that big swoop is. That's us going through perigee and seeing this large, we call it the, I can't remember exactly what to call it, but anyway, it's all about the fact that we're moving rapidly relative to the Earth's magnetic field, and there's an electric field in that frame of hundreds of millivolts per meter relative to sort of the geophysical stuff that's maybe a few to tens of millivolts per meter at that altitude. And so for us, so in the near real time data, we don't have the ability on board to correct and subtract that away. And so near perigee, the space weather electric field data is not that interesting and not that useful. Further out, these sort of more fuzzy parts, that's actually where we're near apogee, and you don't have, the spacecraft's not moving as fast, and the magnetic field has fallen off by 1 over r cubed at least. And so again, this sort of motional electric field due to us moving relative to the magnetic field drops way down, and you can actually see the actual fluctuations that are due to geophysics as opposed to just orbital motion and special relativity. And so once we get this cleaned up and fixed up, that'll be nice. Now the other panel here that Dan scrolled down to is it's marked as the electric potential. What this is, and if we have time and we get into the CDAWeb stuff, we've got an example of this. This is actually a measurement of how different the voltage of the body of the spacecraft and our electric field probes is. And it turns out that because of the way that we operate the probes, this is a really nice measure of what the plasma density is around the spacecraft. And there's some really cool structure that you can see in this orbit after orbit as we go out from the lower density or the high density regions near the Earth out further towards the low density regions. There's some really nice abrupt boundaries that you can see. And if we don't get to it this time, we'll take care of it the next time that we meet. So, but anyway, just some background about that. And again, the issue here is, how do you guys make use of this kind of abstracted data to talk about what's going on? And some of it is just sort of looking. You can use it to introduce different sorts of patterns and structures that exist with radius around the Earth. Kind of like what Vic was doing, sort of saying, how do these different energies of particle flux lay on top of each other in radius and produce the standard belt structure that we talk about. So anyway, that's just sort of give you a little bit of orientation on how you might use this. So
I got a question for you on that. Is if your frame gets electrified as you move closer, for example, you go through a magnetic field.
Yep.
That a few years back, that concept of the tether to obtain an electric source was not that far-fetched then. Is there enough voltage to really be usable?
There can be. I mean, the biggest issue is that you in essence are stealing energy from your orbital motion, and essentially you're running a generator off of your orbital motion. And so for large scale structures, large scale conductive structures moving across the Earth's magnetic field, if you can make a good electrical connection to the plasma, which it really depends on what the plasma conditions are at the two ends. Basically at the inward and the outward end of your spacecraft. You get a sheath forms, and you have to collect electrons at one side, and you got to collect protons at the other side, or other positive ions. And so you can definitely pull power out of your orbital motion and use it for actual electrical power. Conversely, and there's actually a really nice short story by David Brin that was written back in the early days of the shuttle program, and it's a story about a space station built from the old external tanks. And there's a whole sort of rigmarole that they're going to get shut down. But what they do is they run power through their tether the opposite direction, and basically take electrical power and use it to spin themselves back up and pull their orbit up very slowly. It's not a very efficient process, a very fast process, but it was enough so that they could make themselves independent of the government at that point. It's kind of a nice libertarian sort of thing. But anyway, it's also just such a cool piece of like hard sci-fi where you can take it and then use it to say, how does this work? How can you make it work? And is this actually true? And the answer is, yeah, you can do it. And it's a real effect. You got to worry about it when you're putting large structures out in space. Does that answer your question, Vic?
Yeah, and I'm sitting here thinking, you talk about conservation of energy on a big scale or a small scale. It doesn't matter. You have to conserve it. You don't get nothing for nothing.
Exactly right.
There's going to be a price to pay. And I like this one because you can see and think.
Right, exactly. You can see and think about how it all works out. Well, that's interesting. That's actually something that I hadn't really thought about. For us, this we call it the V cross B, or the motional electric field. It's a systematic error that we have to, or a systematic bias that we need to account for and subtract off to get to the geophysics. But it's actually, it's a real electric field that has electrodynamic effects on things when you go through perigee fast like that. And so, as a point of departure for talking about what goes on, for real things out in space, it's actually kind of a cool thing. I hadn't thought about that. That's cool. Thanks.
What do you think, John? Should we try and get to the CDAWeb stuff? We got about a half hour, right?
Oh, we do? Okay, yeah, we do have a half hour. So yeah, we can certainly jump into that, and I think that we'll do all right. I think it's, as long as you're comfortable with it, why don't you keep on driving? And
yep. When we did this in the dry run, and I drove while you spoke, I thought it worked out pretty well. That way you don't have to think and move your mouse at the same time.
I know, because it's really hard for us Californians to do that.
I have a hard time with it.
Yeah, but you're 3 hours earlier, so you've got plenty of time to think about it.
That's true. Anyway, excuse me, on this screen that I'm scrolling down here, this is just the rest of the space weather data that as you can see, there's, what did I go by? I went by the emphasis data. There's RBSPICE, there's REPT and HOPE and MagIce. We even have something from RPS. So it's all there. But what I would like to show next real quick before we jump to CDAWeb is this is all the space weather beacon data. So very gappy, not to be used for actual science, just to see what's going on right now. But we also have, from the gateway, we have a little tool that gathers up as best it can all of the different instruments, and they publish summary plots whatever their latest data products are. And we try to grab those, and so we have this tool here. And you can see already that for some reason I can't get the ECT plot. I think that they changed their file names, and so Rob needs to change the script so it grabs the right things and the right file names. But the next thing here is, again, here's a more complete data set, right? It doesn't have those weird gaps because this is the actual science data, not the space weather beacon data. And
Yep.
This looks like your data, John.
That is, yeah, exactly. So this is, you know, so what we've got is a couple of different versions of our electric field estimates. And here what we've done is we've tried to remove that motional V cross V electric field as we go through perigee. And you can see that we've knocked it down quite a bit, but there's still some residuals in there that, you know, that we haven't got rid of all the way, either because we haven't tweaked our antenna factors quite right, or, you know, there's small rotations. You know, essentially, you're subtracting off a fairly large signal, you know, and trying to get down to a 1% accuracy, and that's not particularly easy. You know, the difference here between the top two panels and the next two is just time resolution. The top two panels are at about 11-second cadence, and what that is we've done a spin fit. We've looked at the measurements over a whole spin of the spacecraft and fit a sinusoid with an offset to it in order to get a low frequency, high accuracy estimate of the electric field. The next one down, you know, what we've done, that's at the full 32 sample per second. And what you can see there is that, you know, the biggest difference is the fuzz. You can actually see stuff up to about 16 hertz in this plot, and, you know, probably not at this resolution, this is a full day's worth, but you can see that there's all kinds of interesting stuff going on at sort of the few millivolt per meter level or even higher. You know, this is a particularly quiet time. So, and then the next two panels are, that's interesting, I don't know what those bottom two panels are, but the two panels that are sort of the V1 plus V2 over 2, those are the spacecraft potential that I was talking about. And we've got them split up in two places. One is the top one goes from 0 to 200 volts. And what that does is there's particular situations where the spacecraft will get immersed in a big flux of electrons, a very high flux of electrons. And what that does is it drives the potential of the spacecraft negative relative to our probes. And so because we're measuring our probe potentials relative to the spacecraft, it shows up as a big positive excursion in this thing. And so it's a way for us to see, you know, when we go up onto that plot and we see a big jump in that, we know that we're in an interesting physical situation. Now, typically, however, the variation is more like this, more like, you know, where this potential is negative. The spacecraft is positive relative to us, and so us minus our sensors minus the spacecraft is a negative number. And this variation in potential is essentially proportional to the logarithm of the plasma density around us. And there's a bunch of current collection physics that goes into that. But what you can see over the course of the orbit is that you get orders of magnitude changes in the plasma density. Essentially, it's about an order of magnitude or two change per volt. And so near perigee, the density is high, and then you have a fairly abrupt shelf as you move away down to a much lower density out in the magnetosphere. And what that is you're moving out of the high density plasma sphere in passing through what's called the plasma pause. And the plasma pause can be sort of gentle, it can be much more structured, it can be, you know, if you go over earlier in the day, you can see that there's actually, keep on going to the inbound pass right there. You can see that actually there's some abrupt stuff and actually a separation of a chunk of the plasma sphere away from the main plasma sphere. And that's actually it's a really cool thing. You get these big plumes of plasma getting peeled off and then convected up to the front side of the magnetosphere to participate in things going on. So there's a lot of stuff that you can diagnose with a really simple measurement, you know, from our instrument. So anyway, enough about my instrument. There's some really beautiful stuff that comes out of the emphasis instrument. which is shown down here. They do really beautiful spectral analysis on board. And what this is you're sort of seeing in the top panel, this is a spectrum that goes all the way up to about 500 kilohertz. And then the next panel down goes up to about, I think it's 12 kilohertz. And those are both measurements of the electric field. And then the bottom one is it's a measurement of the magnetic field. And again, it goes up to about 10 kilohertz or 12 kilohertz. And I think the thing to sort of look at here, and I'll show you this in the CDAWeb stuff, is if you look, for example, in the top panel, there's that bright line that sort of moves along. Yeah, that's it. Okay, that line looks very strongly reminiscent of what the plasma density was doing in the spacecraft potential. And that's because that line, that particular spectral line, has a frequency. It depends on the magnetic field strength and on the plasma density. And so it's a way that you can get a calibrated measure of the density, and then it serves as a dividing line between certain modes that can propagate in from outside the magnetosphere. So, for example, here when we're out further away, there's a bunch of harmonic stuff down below. But then there's all sorts of this banded stuff that's up above that line. Most of that is things that are being generated further away and are propagating to us and being received as electromagnetic radiation, as opposed to stuff that's being generated locally. And so it's more diagnostic of what's going on as opposed to being geophysically relevant to what's happening right at the spacecraft. But again, there's a huge zoology of stuff. The Iowa guys can talk about all sorts of different kind of stuff that they've identified, through 40 years of flying this kind of instrument. And again, some of it is directly geophysically relevant to what's going on with wave-particle interactions in the magnetosphere. Some of it is more diagnostic of things that are happening out in the solar wind or further away. But it makes for it's visually striking, and that's one of the best things about it. So, and then there's more with the particle data.
It looks like RBSPA there. I'm not sure why there's every other one is missing, but we grab whatever they happen to have at the time, and sometimes there's they've only got half the stuff up or whatever. We're missing a few different plots.
That's right. I mean, and as Dan said, what the Science Gateway is doing is it's taking and it's grabbing the daily summary plots that each of the instrument teams is generating, and depending on exactly how the data pipeline is going, what mode the instrument is in, whether there's been any, and also what the magnetosphere has been doing, whether that's causing any issues with instrument operation. They may or may not release the summary plots because they look at it and go, wow, this is going to be just confusing rather than illuminating. And that's one of the responsibilities that we have on this mission is we have to provide the data in an open fashion, but we're also supposed to vet it. And so it's a fair amount of work.
And when you come here, you can choose the day you want to look at too. Like that was a storm day, right? March 17th.
Our stuff goes to pot there when the storm is happening, and when we get into this charging event, our instrument isn't, the sensors are not biased correctly, and so we have trouble making the electric field measurement. It causes lots of problems.
There's one of those giant jumps in the positive voltage you were talking about right there.
That's right. Essentially we get up there all the way, and then it's too much, and we saturate. So then we stop measuring electric fields in any reasonable way. And so anyway, I guess the point of this is that so the individual instrument teams, we provide this as part of our public, these daily summary plots as part of our public interface to the data. And so, scientists that are interested in, say they've made a measurement on another vehicle, on another spacecraft or on the ground, and they want to go and see, did RBSP see anything interesting on this day? and should I then, bother to contact the instrument teams and get more detailed data? This is their interface for doing that. And in terms of how you might use it, I mean, again, it's a way for you guys to show more detailed data from the spacecraft, kind of establish correspondences between what you see in the particle data and the field data, but also, to kind of show people what the process of doing science is, that it is really this, it's a public kind of collaborative thing when it comes to doing these magnetospheric projects, because you've got to call on a lot of different resources to make it happen. And NASA tries to make that happen with the open data policy, and we sort of work our way through how to do it with these sorts of summary plots and other things. So,
should we jump into CDAWeb then?
Sure.
All right. So you can get to CDAWeb from the Science Gateway. We have a link, and let me see. Where is my link? Yeah, SPDF. SPDF is the Space Physics Data Facility, and CDAWeb is a user interface that allows you to grab the data you want. And John already has a nice little walkthrough.
Okay.
Written up for this.
Right. So this is kind of this is the next level that one can go to. If you don't have software of your own to access the data and do analysis and do data reduction, you can go to a place like CDAWeb. This is essentially CDAWeb is it's an archive to which we deliver data, or actually they come and get data from us and make it publicly available. But it also provides an interface, a way of pulling up the data from a variety of different missions, all on a common time scale, and on your own interval. You're not stuck with a day or a month or an hour or whatever it is that the mission decided was the appropriate time scale, but rather you can sort of pull things up. And so what the walkthrough does, it kind of shows you how to do that. And so what we're going to do is we're going to do that for data from the Van Allen probes. So Dan's going to click on Van Allen probes. And again, this is laid out in detail in the walkthrough that's been posted to Wigio. So then you go ahead.
I was just going to say, I'm actually surprised that we got to this site, because it's a NASA.gov site and they don't seem to be closed.
Yes, I was wondering whether we'd be able to get here today or not, and so for some reason it's been decided that it's essential. So anyway, and what you can do is you can pick. There's a whole huge list of there's a long list, several dozen different missions here. What Dan's going through is he's picking out different data types so that we get a good mixture of stuff. There you go, radio and plasma waves. And I think that's it. Yeah. Okay. And you scroll to the bottom and you hit submit. And then you're going to get this intimidatingly long list of data to select from. So the first, and they come up with everything checked, like you want to look at all of it. And the answer is no, you don't want to look at all of it. That's too much to look at. So first you click on that clear all the check boxes. Then we're going to go and we're going to pick out a few things that will be a little bit familiar from what we talked about earlier today. First, we're going to pick some stuff from the MagIce instrument. So that's that one, yeah, right there. And so that's sort of the medium energy electron and ion fluxes. Then we're going to pick some stuff from REPT. And it'll be RBSPA. There you go. That one. So again, this is the higher energy stuff, and we're not going to do that one. Then we're going to go to the EFW stuff, and we're going to pick the RBSPA. We're not going to do the spin fit because that's just kind of obscure, but we'll do the potentials there. So RBSPA, V-Survey, high res. No, you don't want that one. There you go, that one. Yep. Okay. And then let's see, under the emphasis, we want to try and pull up the RBSPA. magnetometer 4-second GSE, not the GEI.
You're right, GSE, sorry.
GSE, there you go. And then keep on rolling down, and we'll pick up the HFR spectra from emphasis. And so that's HFR spectra level 2. Okay, perfect. So there's a whole slew of other things. You know, why did I pick those? Because I've managed over 6 years to figure out which ones I like, but we'll do that. So, okay, in terms of dates and times, messing around earlier today, I found some good ones. So this would be, let's pick the 726. And starting at 08, yeah, there you go, on 726. Yeah, we can go ahead and do, yeah, we'll do the...
You want that at 1800 hours?
Yeah, from 0800 to 1800.
And all of these, all the ones that John chose, they're all listed for you in that walkthrough that he sent out as well.
That's right. Yeah. So I wanted you to be able to. I wanted somebody who was working with the document to be able to try and reproduce what we did today, and then know why we were doing what we were doing. So.
Thanks so much for putting that together. That's an amazing resource.
Okay, so don't punch submit yet. We got to pick some data.
Right.
All right, so first we do mag ice, and we're going to pick the FESA and the FPSA. All right, and then in rep. Say again?
I was just pointing out that's electrons and protons.
Yep.
We're looking at there.
Electrons and protons. And then in the rept, we're going to pick the FESA and the FPSA. Again, electron flux and proton flux. Okay, then in the V-survey high-res, we're going to get average potential from opposing booms. And then from the magnetometer, we're going to get average magnitude. And then from the HFR spectra, we're going to get HFR spectral data. Okay, now we can push submit. And it goes off, and it gets the data, and it does some stuff, and then you have some plots. Okay, so I guess the one issue with this is you get to pick your time interval, but all of the different things that you pick are kind of spread out. There's a lot of decoration around each of them, so it can be a little bit hard to kind of correlate stuff in time. But what you can see here, what I've done by picking this particular interval is I'm basically going, let's see, this is essentially a plot of one orbit from just ahead of perigee to just after perigee on the 26th of July. So if you're looking at this top panel, the mag ice data, the perigee is this is sort of that bar right there. Yeah, exactly. So, and around that bar, so the top panel is the electrons, bottom panel is the ions, and as we go out in time, we start at perigee, we go all the way out, we pass through the inner electron belt, we pass through the outer electron belts. To get to apogee, we come back in through the outer, through the inner, and we're back to perigee. In the protons, we see something somewhat different, and this isn't quite the energy where you would see the belts per se, but you see the lowest energy parts of the inner proton belts, and then as you go out further, this isn't actually the radiation belts. This is more the ring current in the plasma sheet. So you get higher energies closer in, lower energies further out. If we move down to the next panels, so this is the reps data, Here, you get a really clear and nice representation. So again, we start at perigee on the left side, we move to perigee on the right side. You get the two inner electron belts sandwiched right up close to the Earth, and paralleling those is the proton belts in the panel just below. Those are much higher energy, so again, you can see that those are going up to hundreds of MeV, and that's actually those go up into the GeV range, and that's what the RPS instrument works with. And as you go further out, go ahead.
Sorry, I just wanted to point out, while these plots look like those L-shell versus time plots, the y-axis here is energy, not L-shell. And because they look a little similar, but it's a different thing.
That's a good point to bring out. This is, so what happens when you do one of those L-shell versus energy plots is you pick one of the energies, one of the y coordinates on this plot, and you essentially take it and put it on end and plot that as a slice at a particular time associated with the orbit. So you might pick like the 5 MeV on the electrons, and you'd see a bright spot at whatever L shell corresponds to the inner belt electrons, and then you'd see darkness, and then you'd see a bright blue spot as we go through that part of the outer belt, and then it would go dark again, and then on the inbound pass, you'd see that pattern repeated the other way. And with the protons, you'd just see a bright orange spot at low energy. Say you're doing the 50 MeVs. You'd see a bright spot at low L shell, and it would drop off monotonically as you go up towards apogee, and then it would come back up again as you came back in towards perigee. So that's a great point. That's a really good point. Again, one of the things that scientists do is we get so used to how we represent data that we forget to introduce it to newcomers. And one of the best pieces of advice I ever got from advisors is always introduce your plot axes, because otherwise people are going to be confused. So anyway, so this particular orbit, if we go down to the next one, this is again that sensor, the spacecraft potential estimate. This has a whole lot of really nice structure to it.
Yeah, look at that.
Where early in the orbit, you have this very smooth, gently varying changes in spacecraft potential that are associated with smooth and slowly varying changes in plasma density. But then as you get further in and you're in a different local time sector, there's much more abrupt changes. So we go through a very dense area. This is probably, again, one of these disconnected plumes. And then we go abruptly down into low density regions that have some structure to them. And then back right into a high density region. There's all sorts of really cool stuff that's going on. And the next panel down, again, this is all I'm showing here. There's two of them here just because we have two sets of sensors in the spin plane, and we wanted to show both measurements, because sometimes one set of sensors will saturate and the other don't, and so it's a way for us to verify the quality of the data. Again, the next panel down is showing the magnitude of the magnetic field in the spacecraft frame, and the biggest thing to see here is how much the magnetic field changes as you go from perigee out to apogee. And you start out here at about 23,000 nanotesla, so 20 microteslas, and that's almost, the field at the surface of the Earth at the Earth's equator is about 30,000 nanotesla. Why do we count in why do we count in thousands of nanotesla? Well, the field strengths when you get further away from the Earth are very conveniently measured in nanoteslas, tens of nanoteslas or hundreds of nanoteslas, and so it's a handy unit. But we fall off very rapidly down to, maybe 100 nanotesla when we get finally out towards apogee. And if you compare down to the spectra down below, you can see that there are spectral features that follow that trend, both in the density and in the magnetic field. There's all sorts of abrupt things, like if you look, there's that sort of clear patch, or a patch where there's not much spectral density early on between sort of 9 and 930 right there. If you go up and you look, the the boundary of that corresponds to not so much something in the magnetic field, but something in the plasma density. You know, so you go through a shelf, and all of a sudden you can start to see all kinds of stuff. It's a cutoff that's blocking a whole bunch of wave activity from getting in to that region of the magnetosphere. As you go further out, you can see that there are other sorts of little cutoffs. Again, when the density pops back up there at about 1300, again, you can see a blank patch. You know, you're not getting waves in. There's stuff going on above that that's propagating in from further away. And then when we get into this really structured stuff, the spectrum just goes to, the pot. There's all kinds of stuff going on, lots of different kinds of wave activity going on. So it's probably a very interesting time to go look at what the particles are doing, what's going on, what kind of wave modes are around. So but again, this would be a time where somebody, say, saw a change in DST in their ground measurements or some other changes. They could go and they could plot up this orbit and say, what was going on at RBSP. They could zoom in even more if they wanted to, and look at things in greater detail and decide, should I talk to the scientists and try and get some actual data out of them, what sort of collaboration we can do. So. But anyway, that sort of gets you through what I wanted to show and what's covered in the walkthrough of just being able to pull up particle data on your own without having to have any of the software packages that we use for our own data reduction and analysis. And again, sort of the possibilities, I'm going to let you guys percolate on that and think about how you might want to use that in the classroom. If it's only just to sort of show there's a lot of activity going on out in the magnetosphere, and there's a lot of, and that, that area that you might think of as empty space is actually full of all kinds of energetic particles and electromagnetic fields that are doing lots and lots of different stuff. These are the tools, or these are the windows on that, that allow you to see that's what's happening. If they want to do something a little bit more qualitative and sort of say, when DST does one thing, what happens to the stuff in the magnetosphere, that's another possibility. But anyway, I wanted to give you guys an introduction to it and then let you go off and think about it, and we can see what comes of it. But aside from that, why don't we see if there are any sort of final questions, comments from you guys. Otherwise, we'll finish up.
I'll make one comment, and I'll be real honest with you. You kind of lost me at the end.
No problem.
But I need to spend some more time on this walkthrough. But what I will tell you is that very beginning with the loops, I'll put that into use tomorrow in my physics class.
Excellent.
Just so beautiful frame of reference on how you change your frame of reference, and the map looks very different. And it's the same vehicle, so I can put that into use tomorrow.
Excellent. That's great. And I totally expect that as we get further into this, the question of how you can hook it in gets harder and harder, because there's there's more and more background to it that turns the the squiggly lines and the pretty pictures of the spectra into something that's actually meaningful. And we can work with that and see what makes sense.
Thank you so much. This was wonderful. Does anybody else have any questions? We're about at our stopping time. I wanted to make sure that no one else had questions before we say goodnight.
Well, I can't wait to watch what I missed. Sorry I was late. So you were saying that you knew what buttons to push because you've been in there, and you gave us a cheat sheet, which is very nice. Thank you. But you also were looking, and you knew something like this would be interesting to look at. Is it for us just to, by guess and by golly, get in and keep looking and hopefully something will show up? Or?
Yeah, I guess so the question is, is there, you know, in some sense, should we be like sending you guys an alert saying, hey, there was a really good storm that you guys could look at? Is that kind of what you're thinking about?
Yeah, is there a list of, you know, I'm sure that there's a good place that has, you know, where all of the KP index went up high and that we should go in and look around that time, or?
So I do know that we talked about starting a list like that for the mission. I'm not sure if anybody has sort of curated a good list of, you know, essentially like good storms for people to go look at. But you know, Dan and I can talk with the project science team folks, and because I think that there is a list that, you know, even if it is informal, that we can provide to you guys so that you can go and start looking at stuff. Does that make sense?
If you look at the screen right now, at the very bottom, if you go back to the Science Gateway website, so this one, there is a link here. It says List of Van Allen Probes Projects. And I clicked on that, and it actually has, you know, different scientific studies people are doing, little web pages about it, and there's a section that says data, data from, you know, like, and then a date. And so those are probably good places to go look at those dates. If you find, if you look through these different places, these are probably the dates under that section is probably telling you about some interesting time. So that might be a good place to look.
Okay.
The other thing you can do, of course, is like in our Juno flyby here, I scrolled down to the bottom. I apologize for not being able to see the very bottom of this, but you can see all kinds of what the radiation belts were doing from the beginning of the mission. And so you can kind of take just if you can see the very bottom, actually you can see right here the time scale. Even that you can go and look and say, oh, it might be interesting to look at the third belt. When did that happen? Well, it happened the first month of the mission. So maybe looking at, you know, at times like that. Or you want to see a space where there's the radiation belts seem to be disappearing. I wonder what else is going on. You know, you could look at those dates. And so that's a way of sort of looking around for yourself to see what might be interesting.
We have access to magnetometer data very easily. Could we use that as a trigger point to say, well, when the magnetometer says we have a CME bouncing off the Earth, would that be the time to, hey, these might be some dates that interesting things could be happening?
Heck yeah. Absolutely.
Yeah, I mean, essentially you all's sort of mid and high latitude magnetometer stuff is very much akin to the KP index.
Okay.
Also, on the space weather page, we plot the KP index and DST and what the solar wind is doing on any given, you know, and you can go back and click through there and look on any given day as well. So there are places to go explore just to look for those things. But whenever you see KP like this is up around 6, or it gets up to 8 in some cases, I think if we go back a couple of days, I might see it at 8. Then you know there's something interesting going on. So that might be a good time to look. Of course, the science data is delayed by about 15 days or so. So stuff that just happened now, you're not going to be able to rush out and grab the science data to look. But you can go and look at the admittedly spotty, but it's there, space weather data. If you want to go back and look at storms that already happened, then you can go and look at all of the actual data that's available at CDAWeb, and you can put in the dates you want and look at those places.
Thanks, guys.
You're welcome.
You're very welcome.
Oh, thank you very, very much. It's fun to listen, even if I don't understand half of what you're talking about. It's still fun to listen what's going on out there.
You know, my wife does not agree with you. I think the phrase is that a sentence for NASA, or are you trying to tell me something? Anyway, yes, and it's a pleasure talking with you all. I hope we can do it again soon.
Be great.
Thanks. Bye-bye.
Thanks so much, you guys.
Bye-bye.
Bye.
Have a
Bye.
good night.
Thanks, everybody.
John and Dan, that was awesome. Thank you so much again. This is really cool. I enjoyed it.
Oh, you're welcome. So I don't know what do you know what the plan would be? You know, are we going to have more of these meetings?
I would hope so. We don't have anything scheduled right now. We have some things. We have a meeting that has yet to be scheduled, but we'll be scheduling soon to talk about how we want to take the community of practice forward. So I think that meeting is going to come up in the next couple of weeks. We need to, we have a poll out with the teachers right now to figure out what the best day for them will be, and then that'll be scheduled.
Okay,
so after that, we would love to have you back. This was really cool.
Okay.
You're welcome to join us whenever you like.
Anyway, well, thank you, and it's been great. You know, working with Dan and Rob last week, it was really good sort of walking through the Science Gateway and coming up with that piece of it too. I think that's, you know, as Vic said, that's a really approachable section of this whole thing. So for them. Anyway, I'm going to bail. Good to see you all.
Good working with you, John. It was fun.
Yeah, exactly, man.
Yep. Thank you very much.
Bye, Vic.
Bye, you guys.
Bye, everyone. See you, Dawn.
Bye.
Bye, Nick.